So from the name, you can guess partially what the problem we are going to solve. All right. So let's look at the problem first. Our problem number 17, binary exponentiation problem. Yeah. So we did one simple example before. So you can recognize it quickly. Given a real number a and a positive integer n, find the value of this expression a to the nth power. All right. So this is the general problem. Yeah. Recall, I give you one such example before in our exercise 1, question number 23. I ask you to calculate this expression, a to the a times x to the 9th power, and in my solution, I did in this way. All right. So here you can see I organize the data in this special way. So it's a very special. Then we count the number of multiplications. Yeah. Because the goal is using the minimum number of multiplications. So find this in the most efficient way. Yeah, here I do not say that, but in our algorithm class, we want to find the most efficient algorithm. Here we want to do the same thing. So that means we need to use the minimum number of multiplication. That's our goal. Okay. All right. So here you can see in this special way, let's count. Number 1, multiplication. Then square number 2. Another square number 3. Then number 4, number 5. So the answer is 5. Yeah. Here we use a special technique called a repeated squaring. Yeah. So I mentioned that in class before. Yeah. So that is using the square operation. We can double the exponent. Yeah, exponent double. Okay. Yeah. Square operation. So let's say x m square. We double the exponent, x to the 2nth power. Okay? Yeah. So we use this special property. We try to minimize the number of multiplications. All right. So here, look at this word double. Is there any special meaning in this double word? Yeah, there is something special here. It relates to binary expression. Double, binary, right? So they are related. Double and a binary, they are closely related. So this operation should relate it to binary expression. Yeah. So we want to explore that. Next, binary expansion of exponent. Can we represent the exponent number n in the form of a binary expression? Yeah. So we can do that, and then we see if that helps or not. Yeah. Here we don't, at this point we do not know if it helps or not. All right. Why using the binary expansion? Okay. So here, the repeated squaring technique give us a hint that it could relate to the binary expansion. Yeah. But we need to investigate more. Okay. And we want to solve the general problem, not a special. So, x to the ninth, special. Now we need to solve x to the nth for any positive integer, general. Okay, all right. Yeah, so let's try to expand a given integer as a binary expression, bits. So, we use the bits to represent given integer n. All right. Base 2 expression. So that is the base 2 expression. So we can write it explicitly in this way. Yeah. Base 2 representation. All right. Yeah. So we're familiar with this representation. Yeah. All right. But this form looks quite familiar. Yeah. So we studied a similar form before. Yeah. So this form, remember when we studied the polynomial evaluation before, right? Yeah. Our problem 1, evaluate a polynomial. In that problem, we consider a polynomial in this form. Yeah. Now you can see how close they are, right? So that n actually is a polynomial at a special value. So what special value? 2, value 2, p of 2. Yeah. And this polynomial, we have an efficient algorithm, Horner's rule. So here we have an idea. Can we use the Horner's rule to solve this problem efficiently? Yeah. So here we get that hint, Horner's rule to solve this problem. All right. Now let's recall the Horner's rule. Using the Horner's rule, so we know how to evaluate p of x efficiently. All right. So now for this exponential function, all right, yeah, a to the p of 2. Yeah. Then we write in this way. You can see, yeah, this way. Yeah. Still, it's hard to connect to the Horner's rule, right? Yeah. Still, we need to, if we write in this form, yeah, because based on the property, some property of exponential multiplication with the same base, right? Same base, yeah, a. So we have this result. Then, because each one you can see related to the repeated squaring. Yeah. Because for this part, you can see every time you multiply the exponent by 2, you are doing the squaring operation. Yeah. So let's take a general term of this. So when we evaluate this general term in our, exponential function expression, we have these two cases. Yeah. When bi equals 0, we just multiply by 1. That means we do not need to do multiplication, because by 1, that's the same number. We do not want to waste one multiplication for this. Yeah. But when b equals 1, so you only have power of 2 at the exponent, that's square operation. Yeah, power of 2. So you keep doing square operation. See? Yeah. So here you can see we have some chance to organize our data in a special way so we can reduce the number of multiplications. Yeah. Let's see. How do we, try to connect our current expression to the Horner's rule? How to do square operations efficiently using the Horner's rule. The Horner's rule, can make us evaluate polynomial using the minimum number of multiplications. That's Horner's rule. All right. So for this polynomial, when we evaluate it, we do this special way. This is the Horner's rule. Okay? Yeah, so we're familiar with this evaluation. All right. Then P of 2, so we write in the same way. See? Same way. Yeah. Next, we do the calculation. All right, so we can write like this. How about this? Okay? Yeah. So here, after we write this, does it help? So we may ask ourselves, does it help this whole complicated expression? How does it help us? Right? Yeah. So here, we still not that obvious at this point. Still, how to evaluate efficiently is still not that obvious. Yeah. So here, there is an issue. How to organize the data. That is very important. Yeah. So here, if we see if the data is very messy, so then we cannot use our data efficiently. So we try to, rearrange, reorganize, try to, using our data in a very smart way. Then we can get a good result. All right. Here I want to use another important method. It is called a decision tree method. Making decisions. When we make decisions, we can draw a decision tree that can tell us some useful information. Yeah. So let's do that. Decision tree. All right. Let's use decision tree to reorganize the data here, because the data looks messy. So we want to organize it in a nice way. So here we use the decision tree. Making decisions. Here, look at how many decisions do we need to make. Okay? So at every step we need to make decision, right? Yeah. So here, let me point out the decisions. Otherwise, you cannot see where are the decisions, right? Where are the decisions? All right. First, what is the value of BI? The most significant bit in the binary expression of n. There must be 1, right? That cannot be 0. If it is 0, we don't use it. Why we use it if it is a 0? So it has to be 1. Okay? Yeah. So if it is 1, we do not need to make any decision, right? Because it is already 1. What decision do we need to make? We don't need to make any decision. All right. But next, BI minus 1. This could be 0 or 1. This one we need to make decisions. There are 2 possible decisions, 0 and 1. So that's the meaning of decision. Okay, 0 or 1, two different decisions. Okay, so each bit, two different decisions. Yeah. Then we can draw a decision tree. It's a binary tree. It has two decisions. It's a binary tree. Okay, yeah. Let me draw that explicitly. First, a to the I, because bi equals 1, so we do not need to make decision. We just start from there. Okay. Then, when we go to the next level, we need to make a decision. Okay, so next level, when we need to evaluate a to this power expression, okay, so we need to use the value of bi minus 1. Here we need to make a decision, because bi minus 1 could be 0, could be 1. If it is 0, this expression becomes a squared. Yeah, because bi minus 1 is gone. Okay, a squared. For the other decision, when bi minus 1 equals 1, so then this expression becomes a squared times a. Okay, so here you can see, here we need 1 multiplication, here we need 2 multiplications. Okay, all right. After that, when we go down to next level, we need to make another decision. bi minus 2 equals 0 or 1. Here, similarly, bi minus 2 equals 0 or 1. Two decisions. All right. But here, we want to combine these two nodes to one expression. Yeah, because otherwise, we need to do the decisions, similar decisions twice. So we want to save. So similar decisions twice. Why we need to do that? Right? So that's why we want to combine these two cases in the general term. In general term is a to the pth power. The p could be 2 or 3, right? 2 or 3. So, but this is the general expression. Then from here, then we make our next decision. Okay? Suppose the next decision, we want to evaluate a to the 2p plus bi. We need to make two decisions. bi equals 0 and bi equals 1. Two decisions. Okay? For the 0 case, square corresponds to 1 multiplication. For 1 case, square times another a corresponds to 2 more multiplications. Okay? So that's our decision tree. That's the way we use the decision tree to organize our data. You can see after this way, it looks like we can do things quite different. Yeah. Let me make summary here. Okay. So make the picture, better organized. Yeah, summary. All right. First, for the initial values, p equals 1, initial value. Yeah, because the most significant bit always 1. So we start with p equals 1. I equals capital I minus 1, because the first bit, the first unknown bit to be considered is this one, I minus 1. Okay, all right. Then we do the calculation. Okay. Yeah. All right, so we calculate this expression. How to calculate? So remember here we are doing the calculation of two cases. Yeah, so we do the calculation. After the calculation, we need to update our p value. So this expression, we use it to update the p. Okay? Yeah. I also updated, decreased by 1. Yeah. Get next I. Yeah. After that, then we go back to do another evaluation. Okay, so we keep doing that, but we need to stop somewhere. So we need to set stop point. Stop after I equals 0. When I equals 0, we still do the calculation. Yeah, because we have B0 number, right? We still do the calculation, but after that, then we stop. Okay, yeah. So that's the workflow we need to do. Okay, so based on this workflow, all right, we can write our program. We can implement this algorithm in our program. Yeah. Here, so let me just use some examples to go through this whole procedure. So let you see how do we use this procedure to solve this binary exponentiation problem. All right, example 1. N equals 13, a to the 13th power. Yeah. First, let's represent 13 as a binary number. So this is the binary number. Yeah. I think you can do it easily. Okay? Yeah. So you can do it by yourself. You can figure out by yourself. Okay? Yeah. This conversion. Yeah. After that, then the work to organize our work, I draw a table to organize. So BI, we can list 1101 from the most significant to the least significant bit. Okay. Then P value, yeah. At the beginning, P equals 1. Then every step we update that P value. Then A to the 2P plus BI power, yeah, because every time we need to evaluate this value. So we also put it here. Okay. Then we also count the number of multiplications we need. Okay. And we use the accumulative way. Yeah. So we accumulate. Every step we need to add a few more. Yeah. The current total, and at the end, we get a total number of multiplications. Yeah. All right, so let's do the work. All right. First, look at this BI minus 1, right? It is 1. Okay. It is 1. It tells us 2P plus 1, right? Yeah. So this is the initial value. So always, yeah, 1 from the most significant bit, also 1. Yeah. Then, because it is 1, so we have a, when we see 1 non-zero, square and times another base number. So 2 multiplications. Yeah. The P update. 2P plus 1 is 3. So we update the 3. All right. That's the first step. Second step, we see 0, we take square. When we see 0, we take square. Right? So the square of the previous a to the pth power. So a cubed square. Accumulative, yeah, because we add one more multiplication. So accumulative count number 3. And p number 2p. Yeah, 2 times 3. 2 times 3, so 6. Yeah. So that's the next round. Next, 1, so 2p plus 1. Yeah. So square of the previous 1, then times the base. So a to the 6th, then whole thing square times a. Okay? So the p, 2 times the 6 plus 1. So 13. Yeah. And accumulative, because we need 2 more multiplication, adding to up to 3, so we get 5. So the answer is 5, you know, for this problem. The answer is 5. Okay, so that's the first example. Yeah. let's do another example. Example 2. So we use a larger number, 45. First, let us write 45 as the binary expression, like this. Then, let's do the chart the same way as before. First, we list all the bits from most significant to least significant. Then, let's work step by step. 0, we only take square. So 1 multiplication. Then, our P, double the previous P, 2. Next, 1 square times another A. That's this. Square of the previous exponent, power expression, right? And accumulative count, 2 more, right? So 3. Then the P, 2 times 2 plus 1, 5. Okay? Next one. So you see 1 again, so square times 1. The previous one's 8 to the 5th, then square times 1. 2 more multiplications, so 5, accumulated 5. Then the P, 2 times 5 plus 1, 11. Then you see 0, so you just double, you square the, previous power, so you get this. 1 more, add 1 more multiplication, you get 6. And P, double it, 22. All right. The next one, the last one, it is 1, so square the previous power times another base. That's this. Okay? Yeah. 2 more multiplications, you get 8 multiplications. Then the P, 2 times 22 plus 1, 45. So that's the same number as our N. Okay? So this is the answer. Okay, see? So you can see, using this way, we can use the minimum number of multiplications to calculate this, expression. Yeah. All right. But, so here at this point, you can see we need to do the chart, We need to do a lot of work. The question is, can we simplify this procedure? Because this procedure looks not very compact, concise, short, Yeah. We want to make it as simple as possible. Yeah. So the answer is yes, we can do that in a very simple way. So here, let me show you how to do it in an extremely simple way without this whole lot of work. All right. Before we do that, we need to summarize some rule from our current example. After we get that rule, we can apply the rule to save us a lot of work. All right, so what's that? Okay, you can see. All right. Other than the first bit, most significant bit, we do not look at it, okay? Because it is always 1, so we do not look at it. Then, after that, you look at all the remaining bits. All right. When you see 0, then you need 1 multiplication. When you see 1, you need 2 multiplication. 1, 2 multiplication, because this is a cumulative version. Here we do not do the cumulative version. We accumulate all the numbers at the end, right? So we do not use the cumulative. So you can see, when you see 1, you just put number 2 there. When you see 0, just put number 1. 1, your number 2 there, okay? So 1 here. At the end, you add up all these numbers, you get 8. Okay. That will be much faster the solution will be much shorter. Now, let me show you one example, very quick. All right. Example 3. N equals 181. Okay. First, let's write it in the binary expression, like that. Okay. After that, now let's apply our rule. Okay. The first bit, we do not count it. So let's cross it out. Okay. Then when we see 0, we put 1. We see 1, we put 2. Okay. So we do that for all the remaining bits. Then you add up all the numbers you list here, you get 11. So that's the answer. That's the answer. So that is very short, very fast. But you need to have the rule first. All right, so that's the 4 videos for this class. So we complete our lecture 8. Next time we will start lecture 9.